So in general, in order to say that a reactive system has reached equilibrium, we would have to show that the sum of the stoichiometric coefficients times their chemical potentials are equal to 0. Alright, so we're going to use this fact in order to help us determine when a system is at equilibrium. Alright, so the stoichiometric coefficients are just defined based on whatever the reaction is. But for the chemical potentials, this is where our framework from chapter 10 is going to come in handy. So we know that we could write the chemical potential of a species in a mixture as the standard state chemical potential plus RT natural log of its activity. Alright, if we're dealing with an ideal gas chemical mixture, then its chemical potential we could write as, standard state chemical potential for the pure species, pure vapor, plus RT natural log of its partial pressure over whatever the standard state pressure is, where we know that the partial pressure is just going to be equal to the total pressure times the mole fraction of that species in the vapor phase. For liquids, we write the chemical potential as the standard state chemical potential, but this time for the pure liquid species. So GIL plus RT, and then its activity is written in terms of the activity coefficient times its mole fraction in the liquid. Okay? In any case, those are the different ways we could write the activity. But for right now, let's just, keep it in terms of activity. And what we're going to do is we're going to plug in our chemical potential equations into our equilibrium criteria for reactions. Okay? So what we have is the summation of nu I times that chemical potential. So standard state plus RT natural log of A sub I. All those have to be equal to 0. Okay. Let's now distribute across the stoichiometric coefficient. So we get summation of nu I standard state chemical potential plus, we'll factor out the RT, then we have another summation nu I natural log of A sub I. That's equal to 0. Okay? We'll then rearrange the equation by moving this to the left-hand side and then dividing by RT. Mu I, not, should be an I here. And what we're going to do now is we're going to take advantage of our log rules. So something multiplied by a natural log, you could actually move that to be an exponent in, at the top of whatever's in the natural log. And the other thing I want to write is that these standard state chemical potentials, I sort of kind of wrote it up here, but these are all for the pure species, right? And so those standard state chemical potentials, we could write those in terms of just the molar Gibbs energy for each of the species. And we put a knot here just to say that that's the molar Gibbs energy of the pure species at whatever the standard state conditions are. Alright, but now that I have this set up, what I'm going to do is I'm going to define this summation here, because all we're doing here is we're looking at the, once again, for products, this is positive, and reactants, this is negative. So you're looking at the difference between the products and the reactants. And so essentially, I'm going to define this term here as a sort of delta G of the reaction. Okay? And so the term on the right-hand side ends up being negative delta G reaction over RT. Okay? If I rewrite this equation again, what I have is a summation of IC natural log of AI raised to the new I, right? Because here took advantage of our log rules and made that the exponent. And we know that if we add a bunch of natural logs together, once again exploiting our log rules, you could actually just multiply all those things together. And so in other words, what we now have is natural log. And if we're multiplying a bunch of things together, rather than using a summation sign, we use this pi symbol. So this is just saying we're multiplying all these activities raised to the new I. We're multiplying all those things together. So we have negative delta G reaction over RT. I'm going to take the exponential of both sides. So now I have the product of all these activities is equal to the exponential of negative delta G reaction over RT. Okay? And so what I have here now is this sort of activity product. Right? Literally just a product of all the activities. Right? And we're saying it's equal to the exponential of the negative of this delta G reaction over RT. We give this activity product a very special name. We call it K, and we're going to call this an equilibrium constant. So the equilibrium constant that you've seen since Gen Chem 1 or Gen Chem 2, this is actually where it comes from. Actually, it starts from the reaction equilibrium criteria, and by working through, defining what your chemical potentials are and things like that, this is actually how you derive it. Okay? And so in the end, whenever we talk about an equilibrium constant, this is why we say it's just equal to the product of all our activities. And so in general, once again, because the news for products are positive and the news for reactants are negative, what we end up seeing in our equilibrium constant is that all the activities are going to be on top for the products, and all the activities for the reactants are going to be on bottom. Okay?